All right, so we've got 3 examples. Let's hammer these out. Each of these examples is a u substitution integral. In each of these functions where we're taking the antiderivative, each of these functions has 2 bits that are related by way of derivative. So in this first expression, you notice, or in this first function I suppose, you've got this 1 plus x squared and you've got x. And you can see those are related by derivative because you know when you would take the derivative of the x squared, you'd get something to the degree 1, which is what x is. So here's the deal. Let's just articulate this out. So we have u being 1 plus x squared, which means take derivative of both sides, du equals 2x dx. And I guess the issue with that is, well, of course u was selected to be precisely a carbon copy of what we had in our expression. The du does not necessarily produce precisely what was in our expression. We knew degree 2 and degree 1 would relate by way of derivative, and the degree 2 thing would become a degree 1 thing whenever we took the derivative. But yeah, the issue is in our original function, we've got an x dx, and here we've got a 2x dx. What do? Well, I wish we had just x dx. Well, that's fine. To get just x dx, all we have to do is multiply both sides by a half. These 2 things are equal. Do the same thing to both sides. You'll still get equal things. So a half du would be x dx. And now you have a direct substitution because the x dx that was in your original expression is precisely a half du. So make the proper substitution. What's inside the square root becomes square root u, and what's outside the square root becomes 1/2 du. Now that may be sort of ugly on 2 levels once we boil down to this point. It's still less ugly than our original function that we were trying to integrate to compute the antiderivative of. But what we can do here is say, okay, we've got a constant multiple, no sweat. Constant multiple is unaffected by integrals just like constant multiple is unaffected by derivatives. And then one more step, rather than having this square root u written just like it is, why don't we write this as u to the 1/2? Because that would be helpful because now in the form u to the 1/2, u to the 1/2 is equal to square root u. I mean, just like cube root u is u to the 1/3 or 5th root u is u to the 1/5. Square root u is u to the 1/2. And so when we write this in like so, though, we can take the antiderivative more smoothly. So the 1/2 is going to be on the outside. That goes through unaffected. And now we simply take the integral of everything that was u to the 1/2. We got to increase the power by 1. So that's going to be u to the 3/2. And then in front, we need 1/3/2. But 1/3/2 is just the reciprocal of 3/2. Think with me for a second. 1/3/2 is just going to be 2/3. So the reciprocal of 3/2 is 2/3. So yeah, 2/3 u to the 3/2 plus c. Okay, now to polish this off as a final answer, let's take that 1/2 and distribute it through. So we're going to get what, 2/6? Well, I guess what, a half times a third. Let's just cancel the 2s and get 1/3. That'll be simpler. U is 1 plus x squared. We're going to be raised to the 3/2 power, and now the 1/2 times c, remember c was just a letter to express an arbitrary number which could be added to the bit involving u and still be the function whose derivative would be what's above, because even if you added a constant to the function that would result, you'd still get the same function above whenever you take the derivative because the constant drops off. So the long story short is a half times a constant, a half times an arbitrary number, still an arbitrary number. And here we go, we've got our derivative function. So if you were taking the derivative of this to get back to the original, the 3/2 would go in front and the 3's would cancel. You'd get a power to a half. You'd have to use the chain rule, which would give you a 2x. And yeah, the long story short is you'd end up with the function that we originally started with. Okay, what about this next guy? Well, I claim that whenever you look at this thing and you're trying to take the integral, because certainly we don't have a cookie cutter formula for x squared over x cubed plus 1 dx. But if you notice that there are 2 bits of this expression that are related by derivative, you've got something of degree 3 and something of degree 2, well then you could set u equal to that higher powered thing, the thing of degree 3, and then du would resultingly be of degree 2, because derivative simply reduces a polynomial in degree, 1 at a time every time you take the derivative. But then the issue is, well crap, we didn't need a 3x squared dx, we needed an x squared dx. The u takes care of the denominator, but when you look at what's up in the numerator, I want just x squared dx. But that's actually not that big of a deal, because if we've got 3x squared dx, but we want just x squared dx, we've got equal things here. We can do equal things to both sides, and let's do precisely that. Let's multiply both sides by a third. The 1/3 will cancel with the 3 and give us just x squared dx. And then whenever you write this out, you see, okay, we get integral downstairs u, upstairs x squared dx, that's 1/3 du. So I guess no matter how you want to write this, if we got the u downstairs, we could write a 1 here above it, just so that we enforce the fact that we've got a 1 over u with the x cubed dx, and then we've got a 1/3 du to represent the x squared dx. Okay, now how are we going to make sense of this? Well, like always, the constant multiple goes unaffected by way of derivative, just as unaffected by way of antiderivative. So the 1/3 will just factor out, and now we simply have to take the derivative of 1 over u, which is actually not too bad, right? Because what's the derivative of 1 over, or what's the antiderivative of 1 over u? What function has a derivative of 1 over u? Well, that would be ln of u plus c, of course, because, well, ln of u would give you 1 over u, but so would ln plus 10, or ln plus 20, or ln plus 25, whatever the constant was, it would drop off. So we account for that properly. And now, let's distribute the 1/3 through to get a final answer. We'll have 1/3 ln, and I tell you what, rather than keeping our final answer with u, let's go back to the x cubed plus 1. Now we have to do plus c, but technically it's a plus 1/3 c. But remember, c is an arbitrary number. So 1/3 times that arbitrary number is still an arbitrary number. Problem solved. And now with the last one, let's just rattle through with this. This one, I guess, maybe rattle through, that's maybe too profound of a word here to describe this, because this is maybe a subtle example. But the long story short is there are 2 bits of this expression which are related by way of derivative. If you add in a times 1 here, then you can note that you've got a 3x minus 1, something of degree 1, and a 1, which is something of degree 0. And something of degree 1 and something of degree 0 are related by way of derivative. Derivative simply reduces polynomial degree by 1. So if you set u equal to the higher power bit, namely 3x minus 1, then du is going to be 3 dx. And, well, I guess the issue here is that we don't have 3 dx, do we? We have 1 dx. But that's no sweat, because if you have 3 times what you want, you just multiply by 1/3, and then you get what you want. So when you multiply by 1/3, you get the 1 times dx that you had, and now we just need to substitute in. So what is e to the 3x minus 1? That is e to the u. And what is 1 times dx? Well, 1 times dx is equal to 1/3 du. What do we do with the 1/3? Like any constant, you just factor it out, and then you get just e to the u du. And that, fortunately, is a very nice function to compute the antiderivative of, because that is cookie cutter, and it's e to a letter. The derivative of e to a letter is also e to a letter. We keep the 1/3 in there because, well, it's got to follow through all the way through. The constant multiple's got to go through unaffected, and we've thrown the plus c because we know that while e to the u has a derivative of e to the u, so does e to the u plus 10, or e to the u minus 100. Any constant would drop off when you would take the derivative. And long story short, now to polish this off, let's distribute through the 1/3. So e to the u, that would actually be e to the 3x minus 1. And, well, 1/3 times the constant is still just some arbitrary number, and we've done it. And long story short is each of these 3 cases were not completely cookie cutter u substitution. While in all 3, we had 2 bits of our original function that were related by way of derivative. Moreover, in all 3, what resulted whenever you went from u to du was not exactly what you had in your function, although you could make it what you had in your function if you just multiplied through by the right constant to get a carbon copy of what was needed. And once you make that constant multiple adjustment, that constant multiple is not going to really add too much perspiration to the process, because ultimately that constant just gets factored out, because constant multiples are unaffected by way of integrals, and you can sort of play your way through the integral with that constant multiple just as well.